Hello and welcome to another episode of Breakthrough Dialogues, the podcast for pragmatists and problem solvers brought to you by the Breakthrough Institute. I'm Alex Trembath, your host and deputy director here at Breakthrough. For this episode, I spoke with Zeke Hausfather, Breakthrough's new director of climate and energy. Zeke joined us a couple months ago and is about to complete his PhD at UC Berkeley's Energy and Resources Group. Zeke is a climate scientist and energy systems analyst whose research focuses on observational temperature records, climate models, and mitigation technologies. And he's also worked as a data scientist and entrepreneur in the clean tech sector, a research scientist at Berkeley Earth, a climate analyst at Project Drawdown, and an analyst at Carbon Brief. You can find Zeke's work all over the place, including more and more at thebreakthrough.org. Zeke, thanks for being here.
No worries. It's great to be here.
So I was thinking about how to start this episode, and it occurred to me that you and I have been talking about, and you writing about the 2-degree target, the 1.5-degree target a lot lately, as has everyone really in the sort of climate and energy space. And it occurred to me that I've sort of been aware of the 2-degree target or the 450 parts per million target since as long as I've been paying attention to this stuff. But much more recently, we've been hearing about this relatively newer 1.5 degree C target. So I want to ask you sort of in some detail where that came from.
Sure. So the 1.5 C target, unlike the 2-degree target, didn't really come out of a long process of the international community, or for that matter, the scientific literature. 1.5 primarily came out of negotiations during the Paris Agreement, specifically where a number of Small Island nations who are concerned that 2 degrees would lock them into sea level rise that would make it difficult for their islands to remain inhabitable, pushed for a sort of a coalition of greater ambition to have a goal within the Paris Agreement, not just to limit warming to well below 2 degrees, but to push for limiting warming to below 1.5 degrees. It's important to mention that when we're talking about any of these targets, we usually use the terms like well below or below. The problem is there's deep uncertainties in the climate system, and it's hard to create mitigation policy that leads us to get exactly to 2 degrees, for example, because of uncertainties in things like climate sensitivity. And so the way these targets are usually defined is, for example, when people say well below 2 degrees, they mean having roughly a 66% chance of avoiding more than 2 degrees warming based on the uncertainty, by 2100, I should say, based on the uncertainty in the climate response to increased greenhouse gases.
Right, so we might, for instance, reduce emissions to close to zero by later this century, and we don't really know with much certainty what temperature that'll get us to by 2100. How big is that uncertainty?
So the uncertainty grows, of course, as you release more emissions, but even under a high mitigation scenario where you're limiting warming to below 2 degrees, you're still probably going to have a range of between maybe 1.6 and 2.2 degrees as possible outcomes in like the 5th to 95th percentile range by the end of the century. And again, that's because of this uncertainty and how sensitive the climate is to increased greenhouse gases.
So the IPCC releases a report on the 1.5 degree temperature target, which, as I recall, and correct me if I'm wrong, sort of mostly focuses on the differential between the impacts of 1.5 and 2 degrees. Is that basically what that report focused on? Pretty
much. And the report itself, was at the request of the UNFCCC, which in this request came out of the Paris Agreement discussions with this aspirational target. So it was sort of an interesting tail wags the dog example of the policymakers pushing the scientists to consider something that, to be honest, hadn't really been considered much in the literature. There's very little published papers, or scenarios for that matter, on 1.5 degrees. And so there's this whole process leading up to the IPCC special report where a ton of people looked at this problem. You had integrated assessment modelers producing models that could reach 1.5C, though they had some challenge doing that, and there was a big debate within that community of how plausible it was at the onset. And as you mentioned, there's a lot of analysis of what are the difference in climate impacts between 1.5 and 2 degrees, both globally and in various regions and ecosystems.
So do you think the existence of the 1.5 degree target or attempts to model what a mitigation pathway towards 1.5 degrees has been illuminating, useful?
I mean, it's been interesting to explore the range of impacts that happen at lower levels of warming, and I think that fills a useful gap in our understanding. At the same time, we're kidding ourselves if we think there's any real chance to limit temperatures to 1.5 degrees, at least in the absence of things like geoengineering or incredible breakthroughs in our ability to remove carbon from the atmosphere late in the century. So, in some ways, the focus on 1.5C is a little bit of a distraction and a waste of time and setting ourselves up for failure when we blow past that target in a few years. But there is some interesting science being done there, better understanding the impacts as we increase warming that hadn't been done before. I mean, at the end of the day, the real problem with 1.5C as a target is you set yourself up with two equally difficult choices. Either you're going to reduce global emissions to zero within 20 years, which, to be honest, isn't going to happen. The technologies aren't quite there to move that quickly. The political will certainly isn't there to move that quickly. And if you want to reduce all global emissions to zero, you run into some really thorny problems about equity and allocation of the remaining pie of emissions in a very short time frame. So that's one option. On the other hand, what you could do is, reduce emissions to zero in 30, 35 years, but suck tons of emissions out of the atmosphere by the end of the century, somewhere around half of what we're emitting today in some of these models. And that requires a huge allocation of land area and and energy to negative emissions. In some of these models, you have 3 times the land area of India being devoted to negative emissions technologies by the end of the century in order to suck up enough carbon to reach this 1.5C target.
Yeah, to me it seemed like a bit of a double-edged sword. On the one hand, we've known since we started studying climate impacts, that we want a better understanding of what the near and medium term impacts are going to be. On the other hand, the way that has been sort of deployed in the sort of popular writing and a lot of the policy analysis of IPCC science and climate science is as a target. And I'm sort of hungry for a way to be able to talk about nearer term impacts without thinking that near-term impacts mean that we need to make the target ever more immediate and ever more drastic.
It's a good question, and one of the problems with focusing on targets in general is the climate doesn't recognize targets, right? Climate change is a problem of degrees, not thresholds, and so the more CO2 we emit, the higher concentrations get, the worse the impacts become, and that's a gradual worsening. It's not like once we pass 1.5 degrees, some crazy tipping point kicks in and the whole world goes to hell. And the same thing is true, to the best of our knowledge, with 2 degrees. And so there's a problem of these targets becoming iconic in a way that isn't really supported by the science. And therefore people start, becoming increasingly despondent or fatalistic when it becomes clear that we're not going to meet those targets because there's not the political will to meet them in the world today. There are some real impacts that happen at certain thresholds. Coral reefs are a great example of this, actually. You can say with some confidence that coral reef ecosystems can survive close to 1.5C warming, but have a much, much harder time surviving 2 degrees plus warming. They're something of a special case. A lot of other ecosystems, the impacts are much more gradual.
Yeah, what are a couple of those other interesting or worrying tipping points, whether or not we have any certainty about where they might take place on a temperature or emissions trajectory?
So there's a number of tipping points that are examined in the literature, and some of them have effects on global temperatures, others have effects on things like sea level rise or local ecosystems. The big global ones that people tend to talk a lot about are the ice sheets in Greenland and Antarctica, the thermohaline circulation, or AMOC, Atlantic Meteor... I actually forget what AMOC stands for. The sort of ocean conveyor belts. There are changes in El Nino events that are expected to happen in a warming world that have some thresholds related to them. There's a few other of these global scale tipping points. But in all cases, there's not a clear understanding of what the threshold would be to tip these systems over a threshold. And even then, the timescales over which changes occur are often quite long. The ice sheets are a good example of this. You can have dynamic ice sheet loss contributing to fairly high sea level rise by the end of the century in high emission scenarios. But the sort of long-term tipping points of, say, a 2 degree plus world happen over centuries, or if not millennia, to really get complete disintegration or large-scale disintegration of some of these ice sheets.
Yeah, I want to sort of pull back a little bit just for a moment and remind our audience, that no matter, we're talking about quite a bit of uncertainty in the climate science and in expected or projected warming. I think it's fair to say that everything that we have learned from climate scientists, from climate science over the decades, leads to the general conclusion that we want to reduce anthropogenic emissions as quickly as possible. I assume you would agree with that, right?
Yeah.
So from sort of a policy and action perspective, I'm curious, what are the really interesting uncertainties within climate scientists that would actually help us better address impacts, better inform mitigation policy, better inform adaptation policy, better inform geoengineering practice and policy and things like that? Obviously, one of the things that happens in these conversations around uncertainty is it could sort of muddy the waters for action, when in fact we know sort of at a fundamental level from a very robust climate science that we want to be reducing emissions as fast as possible. That doesn't mean that we can't and shouldn't be doing more and better science. So what are the sort of areas of climate science in particular that you think would be most helpful to policymakers?
So some areas of key uncertainty in climate science are, the big one is climate sensitivity, right? If we double carbon dioxide concentrations in the atmosphere, is the world going to warm 2 degrees? Is it going to warm 4 degrees? Both of those are well inside the range of what we see in climate models, and are consistent with other lines of evidence we have from the paleoclimate or from observational temperature changes. And so narrowing that range would give us a much better sense of what types and scale of impact we'd have by the end of the century under different emission scenarios. Now, that said, if climate sensitivity ends up being 2 degrees instead of 3 degrees or 4 degrees, it doesn't fundamentally change the types of actions we need to take today around mitigation, right? Climate change with a 2-degree climate sensitivity, if we triple atmospheric CO2, or quadruple it for that matter, is still a pretty terrible world and not one we want to live in. So, these uncertainties are really important and can affect the sort of speed at which we undertake some mitigation adaptation activities, but they don't fundamentally change the need for them, and it's important to point that out. Some other big uncertainties are around sea level rise. There's a huge range of projections in the literature, particularly around the contribution from ice sheet dynamics, so how quickly you have losses from places like Greenland and Antarctica that are still fairly poorly understood. There's big uncertainties around clouds and aerosols, and the sort of indirect aerosol effects that help produce cloud formation. That are one of the biggest drivers of this uncertainty and climate sensitivity. And that's an area that scientists are always trying to better model, especially because climate models, don't usually have the scale needed to resolve cloud behavior in a physically realistic way. So a lot of these things kind of need to be parameterized using, simple heuristics that don't always perfectly reflect reality, and, often have some choice by the researchers in terms of what parameters they put into the models for things like clouds. And then finally, there's big uncertainties in precipitation. We focus a lot on global mean temperature change or even regional temperature change, but there's also a lot of projected changes in precipitation in a warming world. The challenge is the models are all over the place in where those projections are, particularly when you look at average annual precipitation. Some models say Australia will become 40% drier, and some say it'll become 20% wetter. And when you have a range that big, it's really hard to do effective planning for mitigation, for adaptation specifically. There are some robust things we can say about precipitation, particularly that in all the models you have extreme precipitation events increasing. So when it rains a lot, it's going to rain a lot more. But in terms of average precipitation, there's a huge range. And more broadly, getting these global scale model projections down to useful local information is a really big challenge in the space. It's hard to effectively downscale, especially given local differences across models. And so figuring out better ways to do that and better information to provide, city managers and other folks who are going to be doing the on-the-ground adaptation planning is a huge and ongoing challenge.
Yeah, that has been my sense, having dug fairly deeply into the 4th and 5th IPCC assessment reports that, again, we know pretty robustly where global atmospheric temperatures are headed. I mean, they're headed up. We don't necessarily know where they're going to be at any given year, decades from now, but we know they're headed up. We know we want them to stabilize as quickly and as quickly as possible. And we know roughly what that means, that energy and agriculture systems and other human activities need to reduce emissions as soon as possible. And we know here in Northern California, that we probably want to be more resilient to wildfires. We know that in the very long term, the U.S. Southeast probably wants to be more resilient to hurricanes. But then there are these other cases where we're not even sure what the sign of future impacts is going to be, depending on what we're talking about. You mentioned precipitation, and so those are the things that I have sensed could be very useful to focus on and have a better sense of what is going to happen to temperatures in the Middle East that affect crops, or what is going to happen to precipitation in this particular region, in a way that would help adapt and make these places more resilient in the coming decades.
Yeah. Similarly, what will happen to the structure of monsoonal rains in India? Something like that has a huge impact on farmers there. And that's an area where, there's some indication of what will happen from the models, but there's also a lot of disagreement between the models. And so getting better understanding of those sort of things is important. And one of the challenges in this space in general is the challenge of what's called model democracy. So the Intergovernmental Panel on Climate Change, there's a lot of climate modeling done in the lead up to these big IPCC reports. And because the IPCC is an international body, they don't really want to be in a position to say, that Russian model, it's kind of crap. We don't really want to use it for this analysis. Similarly, this Italian model, it doesn't really get things very right. We don't want to use that. This NCAR model we think is really good. We want to put a lot more weight on that. Like, that's the type of thing that, in an ideal world you should do. But it's something that there's been a huge reluctance in the community, particularly in the context of the IPCC reports, to do. And in some ways that gets in the way of, better understanding of these sort of changes. And, this is something that's slowly starting to change. Particularly when you're looking at downscaling climate data, you often are selecting models that perform better in that region than others. But, a lot of people still revert just to the average of all the models or the spread of all the models, even when it might make a lot more sense to look at the models that perform the best at the particular type of climate impact you're looking at, be it temperature, precipitation, et cetera.
Another thing that you have studied quite a bit and that you and I have talked about a lot is the sort of policy response to this science. And I kind of feel like we hear different reactions or different assessments of how policy and climate action are going in the world. So on the one hand, you hear a lot of enthusiasm, I think pretty well-earned enthusiasm, about things like solar and wind and electric vehicles, which we see a lot of today compared to 10 years ago. And there are other success stories. On the other hand, emissions ticked up in 2018, so there's a sense, often quite an explicit statement, that we aren't doing anything, that we've been sitting on our hands for 25 plus years on climate change. So, in broad terms, on policy and action, how do you think we as a country or as a planet are doing?
Sure. So that's an important tension. There are some successes that we really should be celebrating. And the idea that the world would be, dramatically ramping up its coal use and increasing its emissions maybe threefold by the end of the century, seems increasingly implausible today. In many ways, we've moved away from some of the worst case outcomes. And it's a lot more likely that we're on track for a world between, 3 and 4 degrees warming than, say, 4 and 5 degrees warming, in the case where we do no additional climate policy for the rest of the century, right? So there's real steps that have been made that have helped avoid some of the worst case outcomes. At the same time, the scale of changes needed to meet the targets that the international community has set are huge. And we're by no means on track for those sorts of, adoption curves of clean energy and things like that. And so that's the real tension. On one hand, we're slowly moving away from the worst case, toward a world where emissions are peaking and remaining flat or slightly declining, but we're very far from a world where emissions, get to zero by 2050, for example. There's a good report that the UN actually puts out, the UNEP, called the Emissions Gap Report every year, that shows both, this is how far existing policy has brought us from sort of a business as usual outcome, and at the same time, this is how big a gap remains between where commitments are today and the types of emission reductions that we needed to be consistent with with 2C scenarios, not to mention 1.5C scenarios.
So how do you close that gap? A is, where are the sort of technologies, policies, sectors where we kind of just need to accelerate progress? And B, are there technologies, policy sectors where we are almost doing nothing? Sure.
So the easiest place to decarbonize, to be honest, is the electricity sector. There we have a lot of mature technologies that can replace fossil fuels. There are certainly challenges, particularly when you start getting lots of variable renewable energy on grids, but these are challenges that are fundamentally solvable. And the cost curves of the technologies today are moving in a direction to help effectively solve these. Obviously, we're going to have a mix of different electricity generation in different parts of the world. There's no silver bullet technology that's going to solve the problem by itself. But the electricity sector is by far the easiest sector to decarbonize because so many of the solutions are already there. And it's a really important sector because as we try to decarbonize other sectors, a lot of that involves transitioning from burning fossil fuels, for example, for home heating or in internal combustion engines, to using electricity for those purposes. Transportation is a sector that's not quite as far along as electricity generation, but it's one where there are a lot of exciting solutions. We're starting to see the economics of EVs making a lot more sense in many parts of the world. We're starting to see more rapid adoption. None of this is happening fast enough to be consistent with, a 2-degree world, but it's certainly moving in the right direction. There's other parts of transportation that are a lot harder to decarbonize, particularly when you start talking about heavy freight, shipping, aviation is going to be a really tricky one down the road. But certainly parts of transportation are moving in the right direction. Once you get outside of there, though, there's been a lot less work done. So in buildings and both commercial and residential buildings, we've had a lot of discussion around electrification of heat, both water heat and space heating, but there's really not much happening there today in most countries. And the economics are still, a little rough in a lot of places. When we start talking about industrial processes, there's very little that's been done there so far, particularly for industrial heat, which is a really challenging sector to electrify. And then similarly in agriculture, while there have been, steps taken that have helped reduce emissions relative to a world where they weren't taken, we still haven't done too much concerted efforts to reduce greenhouse gas emissions from agriculture. And there's a big challenge in that space, because some things like livestock are just really, really difficult to figure out a way to decarbonize beyond, finding replacements like fake meat.
So I walked through a bit of your resume in the introduction to this episode. You've worked as a data scientist and an entrepreneur, an analyst of various stripes, a climate scientist. I want to get a better sense of what got you interested in this work in the first place.
Sure. So I've always been fairly interested in environmental issues, but really catalyzed my interest in the climate issue was my freshman year of college when I picked up a book by Bill McKibben called The End of Nature. Which was really, eye-opening for me around the scope and the scale of this climate problem. I also immediately read his follow-up book, which fewer people have heard of, called Hope, Human, and Wild. And sort of he had depressed everyone by the end of nature, so he decided to write a book about places that were, pioneering solutions and living in ways that were more sustainable. And so that was a neat counterpoint to that. Around the time I really got involved in campus activism, and this was during the Bush administration, so there wasn't much happening on climate policy or environmental policy in general at the federal level. So a lot of NGOs were pushing corporate campaigns as an alternative. And so I worked with folks like Rainforest Action Network on campaigns against Citigroup, against Home Depot, Menards, Lowe's, Victoria's Secret, et cetera, et cetera. And the weird thing is we pretty much won all of those campaigns. Like all these big timber providers and paper providers agreed to stop sourcing from old growth forests. Citigroup agreed to sign on to the Equator Principles for Responsible Lending. It was kind of a strangely heady time that even though nothing was happening at the federal level, we're winning all these environmental campaigns against corporations. And it sort of showed me that, that activism can be impactful and important. That said, I also realized that I didn't want to spend my life doing activism, per se. I wanted to figure out a way to have an impact on a larger scale. And so I got sort of into energy systems, ended up working for co-founding and working for an energy efficiency startup. And around that time, I got really interested in climate science. I was doing a Fulbright in the Netherlands, and I started reading this new blog at the time called Real Climate by a bunch of climate scientists who then were sort of early career folks like Michael Mann, Gavin Schmidt, Eric Stieg, Stephen Ramsdorff. Now they're sort of the bigwigs in the climate science world. And I started participating in this weird world of climate science blogging. And, back in the mid-2000s, blogs were a big thing. This was before Twitter and, all the other things we use today to communicate. And, that was kind of a hobby for a while. Around 2010, I was arguing with a climate skeptic named Anthony Watts, who runs one of the world's most popular climate blogs. And at the time, he had this sort of conspiracy theory that climate scientists were, picking only the stations that were showing warming and throwing away all the ones that weren't. And his evidence for this was the fact that the number of stations we had available peaked in the 1980s and then dropped precipitously in the early 90s. Now, I tried to point out that that's because Previous to that, we had a retrospective collection of records, and then they set up a network going forward to automatically report. But at the end of the day, I was like, look, if you want to figure out if scientists are being nefarious, just look at the stations that stopped reporting and didn't stop reporting in the early 90s. If there's no difference in trend between those, obviously there's nothing going on in terms of selection. And he's like, well, if it's so easy, why don't you do it? So I wrote up some code to calculate global temperatures and show that there's no difference between those stations. And I was like, cool, that was not too hard. And then I realized that the same code I wrote for that I could use to look at a lot of other interesting climate science problems. Is there a difference between warming rates at urban and rural stations, for example? Ended up producing a blog post about that got read by some NOAA scientists. They reached out to me and said, hey, do you want to co-author a paper on this? Ended up being the lead author on this paper on urban heat islands. Went to a bunch of climate science conferences to present it, ended up publishing it, realized it was a lot of fun and really interesting. And so for years after that, I was doing climate science as a hobby, publishing a few papers, going to conferences while working for my startups. Eventually, I decided that energy efficiency was getting a little boring. There's only so many times you can calculate how much energy a washing machine uses before you want to claw your eyes out. And I was really enjoying my climate science work, and so I decided to go back, get a PhD, and focus my efforts on that. At the same time, I've continued to do a lot of work in the energy space, both around energy system models, mitigation technologies, that sort of thing. And so I try to have a very broad view of both the climate science and the mitigation world.
I think our listeners would be interested in what brought you here. This is a relatively new reality for you, sitting across from me at the Breakthrough Institute. So what was it about your PhD and your years of recent work in publishing that led you to be our new energy and climate director?
So I've always enjoyed doing a lot of work around communicating climate science and energy and policy options around these things. I previously did some writing for Carbon Brief that built a bit of a public profile for myself. And so I wanted to figure out a way, once I finished my PhD, to continue having an important impact and a meaningful impact on the discourse and dialogue around these issues, and not sort of fade back into studying, the effects of climate on the top of a mountain for 10 years, or work as the head of products for a startup or something like that. And so BTI was a great opportunity to really make an impact in the debate around these issues in a way that pushed the dialogue forward and that helped build human prosperity while tackling these important issues and pushing back against some of the both counterproductive solutions out there and some of the growing sort of doomerism among folks. Climate is in many ways the critical issue, or one of the critical issues of our time, and at the same time, we need to be cognizant of the science and what it says, and not, go beyond what we can prove and have evidence for.
In the couple months that you've been here, are you starting to get a better sense of the big questions that you want to tackle?
A number of them, yeah, both in the climate and the energy space. There's a lot of interesting climate questions around tipping points, around the scenarios we use and how practical and feasible those are. There's a lot of interesting energy questions around how best to prepare for a world of high renewable energy, as well as issues around what it takes in terms of energy build-out to meet these climate targets, and many other areas. And so we have a really exciting team of researchers here that are working on all of these, and it's been great to lead them and to produce research.
Yeah, I got to say, I'm pretty thrilled to have you here, pretty thrilled about all of the new researchers who have joined us lately, and looking forward to years of working with y'all in the future.
Yep, me too.
Zeke, thanks for joining us.
Thanks for having me.
And thank you all for tuning into Breakthrough Dialogues. If you like the show, tell your friends, rate us, and subscribe on Apple Podcasts, Spotify, Stitcher, or whatever platform you get your podcast. I want to again thank my guest Zeke Hausfather and our producers Alyssa Kadaman and Tali Perlman. Catch you next time.